we are going to design a beam for torsion. Reinforced concrete sections are also subjected to torsional moments when caused twisting or warping of the section. So some of the common examples are, so if I explain one case of torsion moment, suppose I have taken one beam which is supporting one cantilever beam. One cantilever slab. The slab is subjected to some external forces which will create moment in the slab. Due to this moment, the beam is to carry this moment which is produced in the cantilever slab due to the external force. And due to this moment, one twisting moment also have to be carried by this beam cross section. So in this way, sometimes the beams are to be designed for torsional moment or twisting moment. For a rectangular beam under torsion, the shear stresses developed inside the cross sections in this fashion at the different level of fibers. The developed shear stress is resisted by providing the longitudinal as well as shear reinforcement. The longitudinal reinforcements are provided corresponding to the equivalent bending moment, and the shear reinforcements are provided equivalent shear force. When we design a RCC beam, we commonly design it for two parameters. One is bending moment. The other is shear force. The bending moment mu for Fe 415. This is the ultimate moment or factored moment due to the load acting on the beam, and based on the ultimate moment we calculate the required depth for the beam cross section. Next, the shear force Pu equal to tau b bd. So based on this factored shear force, we provide shear reinforcement. In the design of torsion, apart from these two parameters, you have to add another parameter, that is torsional moment. So when we talk about this torsional moment for design of torsion, so we cannot use this parameter directly like bending moment and shear force. We have to follow some other way to use this parameter. The torsional moment is based on the calculation of an equivalent shear force and an equivalent bending moment. Its effect is added to the actual bending moment and shear force to get the equivalent shear force and equivalent bending moment. To design a beam for torsion, in India we use IS 456. It is an Indian standard plain and reinforced concrete code of practice. So here they have suggested the mid-step method. In this code, in clause 41, it has given limit state of collapse, torsion. It is given in page 74. As per this clause, we have to design the beam. Now, if we follow the IS 456, so in the clause 41.4, reinforcement in members subjected to torsion. So we will find the longitudinal reinforcement shall be designed to resist an equivalent bending moment ME1, given by ME1 equal MU plus MT. So this ME1 is the equivalent bending moment, and this MU is the ultimate moment. So this MU is bending moment at the cross section, and this MT is the torsional moment. That means we calculate the equivalent bending moment from the ultimate moment and the torsional moment. Ultimate moment is the bending moment which we calculate through analysis, and MT is the torsional moment. So torsional moment, how to calculate? Here given one formula. Tu is the torsional moment, D is the overall depth of the beam, B is the breadth of the beam.
Another important aspect for the moment here is, if MT is less than MU, then longitudinal reinforcements are provided with respect to ME only in the tension side.
If MT is greater than MU, then
here ME dash equal MT minus MU.
in this case the effect of torsional moment is predominant and more than the ultimate bending moment, and is assumed to be at opposite to MU. So the reinforcement corresponding to the moment ME dash is to be provided in the compression side. So if I have to show one example, suppose this is one cross section of a beam. So we provide normally the main reinforcement at the tension phase. So in this case we have to provide the reinforcement in the compression phase also, and this reinforcement, compression reinforcement, will be based on the moment ME dash. Like equivalent bending moment, we also calculate equivalent shear force VE, which is given in the clause 41.3.1 of the IS code in page number 75, where VE equal VU plus 1.6 into TU by B. V is the equivalent shear, VU shear force, TU torsional moment, and B is the breadth of the beam. So this way we calculate the equivalent shear, and the rest of the things to follow for the shears are same with our normal concrete design. The next important thing we have to discuss here is the transverse reinforcement when we consider torsion. So here in clause 41.4.3 this formula has been given. Here TU is the torsional moment, VU is the shear force, SB is the spacing of stirrup, Fy is the yield stress, and then you have to know B1 and D1. So what is B1 and D1? Let's see. So this is a beam cross section. So B1 is the center to center distance between the extreme reinforcement along the width of the beam. So this is B1. Center to center distance between the extreme reinforcement along width. This is B1. Similarly, center to center distance between the extreme reinforcements along the depth. So to get B1, the total B minus clear cover in the both side, 2 into clear cover, again minus half of the bar diameter in the both side. Similarly for D1, capital D, total depth, twice clear cover minus 2 into D by 2. As per the code, the total transverse reinforcement shall not be less than this. So that is A as B always greater than equal tau V minus tau C multiplied by B into SB divided by 0.87 Fy. So here tau V is the equivalent shear stress, tau C is the shear strength of concrete, B is the breadth, SB is the spacing of the shear reinforcement, and this Fy is the yield stress of reinforcement. Now this is all about the transverse reinforcement, how to calculate. Now we are going to solve one design problem. So this is the question. The datas given in the question are if we assume clear cover as 20 mm and bar diameter as 20 mm, then effective depth will be.
Now we are going to calculate the longitudinal reinforcement.
First we will calculate equivalent bending moment ME as per the IS 456. Since in this case mu is greater than mt, so therefore there is no need of compression reinforcement. The next step is you have to calculate the area of steel required for equivalent bending moment. Using 20 torr bars as reinforcement, number of bars required. Therefore, we have provided 5 numbers of 20 torr bar as tensile reinforcement for the section. Then side face reinforcement. As the depth of the beam is more than 450, the side face reinforcement is required. Therefore, provide one number of 20 torr on each face. Now we are going to calculate transverse reinforcement for the beam.
Now we will calculate the equivalent shear VE as per the clause 41.3.1. Here we have calculated the equivalent shear stress tau VE.
For M20 grade of concrete, tau Cmax is greater than tau VE. Hence, safe. Next, we have to calculate shear strength of concrete. Now we have to calculate first the percentage of steel for the longitudinal reinforcement. From table 19 of IS 456, we will calculate the value of tau C for M20 grade of concrete and PT equal to 0.92%. Here tau C is less than tau VE. Therefore, transverse reinforcements are to be provided. Now, following the clause 41.4.3, we have to calculate the value of B1 and D1. I have shown this RC cross section. These are the reinforcement in the tension side. In the compression side, I have given two hanger bars or 12 mm diameter. Now, B1 equal the distance between two hanger bars in the direction of width.
There may be a question arise that why we have taken the center to center distance between the two bars in the compression side but not in the tension side. The reason is that in the compression side the distance between the two extreme bar is more than that of tension side. So you have taken the larger one. Like B1, we have to calculate the D1, which is the center to center distance between two extreme reinforcement along the direction of depth. Choosing two-legged tentor bar as stirrup,
We have but as per clause 41.4.3,
the transverse reinforcement should not be the less than the following.
as per the clause 26.5.1.7 of IS 456 2000, the spacing of transverse reinforcement should not be more than the following. We have to know what is x1 and what is y1. So this is the beam cross section. This is a transverse reinforcement or shear reinforcement. These are the longitudinal bars and these two are the hanger bars. So x1 is the total length of the stirrup along the width, means along the shorter direction. Similarly, the y1 is the length of the stirrup along the depth or along the long direction. So when we calculate x1, it comes out as 272 mm. The y1 comes out as 472 mm. x1 272 mm, then x1 plus y1 plus, by 4 is 186 mm.
Finally, we will provide two-legged tentor bars at 100 mm center to center spacing as transverse reinforcement or shear reinforcement. The reinforcement detailing of the beam cross section is shown here. Thanks for watching the video.